So this has not only to do with can we make it resize?
There must be some kind of, this is out of focus. You want to make it zoom?
Yeah.
This is not only quantum relevant, but also relevant for principles in neuroscience, where you have, for example, maximum principles like infomax principles, where you maximize structured correlations in the belief that a natural system tends to maximize some interactions which have a certain structure. So, and I want to show you how to quantify in one example. I don't claim it's the only example. In one example, which we have working on for several years, and define low-order states, which have a specified pattern of low-order interactions. And then in the second part of the talk, I define a distance from the space of low interaction models as a quantifier for high interaction. Yes, distance from low interaction is high interaction. This is the most important thing. And I want to analyze it later. This is the headline.
I think what is
yes, it's visual focus.
Okay. So
the title of the talk was classical and quantum long distance correlations.
Long distance maybe. Yes, it depends on the size. I make a simplified version. I have a chain of bits, capital N bits. Do you have a point?
Yeah, no, actually, we don't have a point, but we could maybe improvise with something.
And so this chain of bits can have correlations. I consider a probability simplex. I can use it's not easy.
Yeah.
We have here a probability simplex, just as usually.
So this is a set of all probability distributions
on a set y, but we use a particular set x, which is just n bit space, and then you look at marginals, which then capture subsystems defined by subsets. This capital N, which is the number of bits, is the number of subsystems. Each bit is a subsystem, and you look at subsystems of subsystems. And you look at their state space, and also you can truncate the sequences. Then there's a theory by Lauritzen, Stephan Lauritzen. He used to define hierarchical models, which are well known. So you define a factor space given a subset V. This is all functions which do not see the points outside of V. So this is the truncated space of V. Here the functions distinguish points, but in the complement of all points which are in V, the function do not care for the values.
So x is the same. X is the same, but y and z are different. So
yeah. For every y and z and z, we get the same value. So the function f does not divide points. It does not recognize anything in the complement of the V subsystem. So what you can do is you select a class of subsystems which are the allowed interactions. For example, you can allow to interact particle 1 is particle 2, particle 2 is particle 3, and that's it. But you can use also higher cardinalities of subsets, and this is class U, which specifies the interaction pattern, and then you sum the interaction spaces F to a hierarchical model, and then you compute simply Lauritzen standard the Gibbs distributions.
So this is a sum of spaces in what sense?
You consider it as statistics. You measure one of these statistics, you evaluate it probabilistically, you compute expectation value, for example.
So FB is a class of functions, is a space of functions.
Yeah. So you evaluate every bit and plug it into the function, that's it. And then the function does not see a part of the system, the function sees only what you specify.
And also, I just want to see this H of U is a sum of this FB.
Yeah, because
and F is the sum is a direct sum of.
No, it's not direct. It has overlap. But this does not matter. So it's an upper bound, and this f, for example, if this v has 2 points, then everything which happens inside these 2 points can be modeled within this f v. And maybe also other things in the H, but everything which happens between these 2 particles can be modeled by this. So then you define the chips family, and well, James has suggested that the points therein they are most non-compromittal towards the information as the expected values of these functions that you have specified. So in this sense, these elements of these chips families, they exactly give you the kind of interaction which is allowed between the pairs you have specified, and nothing else. So, and the main example which goes through now is if you have equally sized subsystems. For example, you allow interactions between pairs, or between triangles, or between groups of 4 people, or ducks. And so, and use a shorthand notation this choice symbol for the subsets of size k in the whole space of bits. And so UK stands for the interactions which happen between pairs of, between subsets of size k. Here's the corresponding exponential families. For example, if we have no interaction, if only point interaction is allowed, then this exponential family consists of product distributions which have no correlation whatsoever. So the Max interpretation to follow it for the special case of these interactions, we need marginals. You can compute for every probability distribution marginal, and then you have a maximum entropy inference map, which is defined on the marginals and assigns a global distribution, which is defined by maximizing the change in entropy. And in this sense, one can easily show that the exponential family of the k-order interaction is included in the maximum entropy ensembles, or in the Gibbs states of interaction order k. And so in this sense, the elements which we have as maximum entropy ensembles, they are the most unbiased choices given the marginals which you have to specify.
Stephan?
Yeah.
So actually this Gibbs family that you say maximum minus entropy, there is f in X, so it assumes that there is also, because it's you maximize entropy with some constraint on, let's say, average value of f.
Yeah, but this is not, yeah.
So is it like, for example, you're trying to maximize the average value of f subject to a constraint on entropy?
No, the average values are given as information.
So f cannot be considered as an objective function that you try to maximize.
No, we don't maximize anything. It's just a model for low interaction, for low degree interaction, but for interaction which allow only pairs, which allow only triples, which allow only subgroups of size k. This is the idea behind the mind. So the image of this map, okay, because you said it's defined by expectation values, in the special case of subsets of size k, you can parameterize the expected values of these functionals by the marginals. And this is done here. So you consider the direct sum of marginals, and then you define a global matrix, and this matrix a global distribution. This distribution, what it does, it stands for the most unbiased choice if you have only information about the marginals of size k. This is it. So this is the best choice what you can make if you allow k-body interaction is to look at the elements of this chips family, or more general at the image of this map. So maybe for somebody this could be too weak to rely on Shannon and chains. Therefore, one can also have a different approach and say, is there not the other way to say this probability distribution captures interactions of order k? Yes, there is one. Many of you will certainly know. Namely, one can factorize probability distributions. Here, p of x factors in a product of terms which depend only on groups of k elements. You know,
For example, like Mark.
this decomposition is not unique. It's unique for k equal 1. Then you have the product of the marginals. We have seen in the other slide before. Yes, but here we have not marginals. These are just functions and they exist. You can compute it actually. You pick a point in E, and then you see you can get a decomposition with a product formula for the probability distribution, which represents its ability that it's confined to order k elections. Subsets of order k, size k elect, you know, bigger subset. So, but can we say something? How does this factorizability relate to the image of the maximum entropy inference? Is it really the same, or is it just a coincidence that this maximum entropy probability distribution do factorize? And actually there is a difference. I want to show you how this difference can be seen. So we have to assign a matrix, which looks somehow odd, but it helps.
Is it the size of a matrix?
So this matrix is actually a parameterization of the exponential family, of the Gibbs family which I showed you before, now in coordinates. For a bit earlier we had no coordinates. And this matrix looks like this. A is equal to A mu y by just x. Y and then mu is a subset of the subsystems, the n subsystems of size k. Then this y is a state point in x, and I forgot this was x. This was the product of the qubits. And this one is in smaller products. And then A ij mu x y is equal 1 if y mu is equal to x, it's zero else. Let's do it for n equals 3, k equal 2, k equal 2. So we have it's 0, 0, 0, 0, 0, 1. Just take a few. The rest is for later. And then we have here the subsets. Let's take subset 1, 2. And the first. Now I'm counting from the beginning. I get here 1, here 1, because this sequence appears at the first place, and I get zeros otherwise. And so it's not here. Yes, it's right. And then we have in the next subset, maybe 1, 3. See, I chose 1, 3. This is here, not here, and here. And then continues. One here. How many do I need? two more. Two, three. I think this is it. Or if you use this matrix, then you can define a monomial map. This is a thing from algebraic geometry, you can say, or from algebra. It's a polynomial map. It's defined like this, and the number of parameters which we have here, it corresponds to the dimension of this exponential family, of this chips family. And this, you can see, this is a homogeneous map. And now we can use some simple algebra, really, it's not complicated. You have to notate the columns of this matrix, because they have a meaning, because they determine at the end which of the entries vanish of the probability distribution. Because by homogeneity of this map, you can compute certain nice formula. And the image of this monomial map in the probability simplex takes this form. It looks already very, very like the exponential family, but it allows also values minus infinity. And this means the support is not maximal. We obtain some of the probability distributions have not maximal support. So this at this moment it's just an algebraic construction, but it's easy to prove, in fact, that all these probability distributions, even if they have no maximal support, factorize according to this formula here. So they have also this nice property of factorization, also they have are not exponential families, not elements of the exponential family. And so this is interesting. What is the difference between, do I have understood the problem right? And Geiger made Sturmfels give a nice definition, which I don't want to show you because it's not good written, not well written. Let me write it for you. This is a nice theorem, which I liked very much. So we take a probability distribution, then P is k-factorizable as a product representation. If the support is k-feasible.
What does mean k-feasible?
I will explain it. I will explain it. And this k-feasibility is equivalent to this strange condition about the minus infinity, because minus infinity is not allowed throughout. It must still be such that the probability has some non-zero entry. Otherwise, it's not normalizable. This is really it. This is an easy calculation which you can give your students if you want. Feasible, that is, for all x in the support, or x without the support P. So this is a complement. We have the column of the matrix A, again the support. I'll extract this to must not be in the union of y in the support of the column of y. again the support. This means that this is the normalization condition that one of the entries should be non-zero. And it's not everything. P belongs to a toric variety.
One of the exponents must be not zero. Yes?
Yeah, exactly.
So otherwise the sum is zero.
Not minus infinity.
Yeah, if you have minus infinity, it's zero.
Yeah, exactly. But one should survive, otherwise you cannot normalize. I mean, this moment is homogeneous. You can always easily normalize. It's no problem. But you should have one entry which you can. After you get some normal probability. Maybe it comes to a toric variety of X. And here's algebraic geometry coming in, such that for all u to v in node d, so d is this strange number of k, 2 to the power of k, the number of columns, with u minus v is in kernel of A. I just write it down because it exists and you have an algebraic approach to interactions. I mean, this is, when I have read it, I was surprised that I saw it. You can use factorization of probability distributions to write factorization probability of interaction structure. This is great. This is the basic of algebraic statistics, and so this is worth writing it down. So the monomial is this. This goes to algebraic statistics. So this gives us a fair thing, and so if we want to see the difference between this exponential family and its closure and the factorizable probability distributions, then we have to look. So this image is at least larger as the exponential family, but the closure is still larger, and so we don't know exactly where is the difference, but this is solved in this theorem. It's not a big step. I want to give you an example because I was working and colleagues of mine have been working on this problem. This example is as follows. It's namely all small subsets of your state space, also sequences, bits, n length bit sequences, a subset of n length bit sequences, which is at most of length 2 to the power of k minus 1, is k feasible. This is proved by Kahle, who has now a junior professorship in multiple. And this shows that such a equipartition, such a Laplace probability distribution supported on this small subset belongs to the closure of the exponential family. On the other hand, it's easy to show that this set is not feasible. I will show you this in the blackboard in a second. And if you compare the dimensions, this set has 3 entries. 3 is smaller than 2 to the power of 2 minus 1. So this is in fact in the closure of the exponential family of 2 interactions, but it does not factorize. And you can see it here in this example. If you take this point, as a set, if you take this set, here's the set which I have written down, and the support of this line, of this column, if you look it up, it's only zeros which follow. It's these 3 points, and 3. Oh, not everybody can see it. This is the support, and it indeed lies in the union of these 3 supports. This one is in the support of that, this one is in the support of that, and this one is in the support of the last one. This is forbidden. This would imply that in the momentum map you get a non-normalizable probability distribution.
So you think is it example showing between closure x, so it's in closure xk, but it is not in which in the left?
Yeah, also I skipped one point where you write nicely to tell me. So it's easy to see that this moment, this image of the moment map, which is the set of factorizable probability distributions, yes, which you can write as a product, it includes the chips family of k interactions, but it's not clear how large it is. It is easy to show that it's in the closure of the exponential family. This follows already from the formula. Just look at this, because you allow some of the thetas of the inverse temperatures to go to minus infinity. It's a limit point of the exponential family. Cannot be more explicitly. But it's not clear how far the differences are.
Okay. So maybe this is something which is a solution to some kind of Rayleigh entropy maximization.
Maybe. Also, I don't know, actually, I'm not sure about it. What it does say is that something strange happens at zero temperatures. So, because where this happens is an extreme far away boundary point of the exponential family at zero temperature. Suddenly correlations appear which are not in the other points of the exponential family, the chips family. So what I wanted to say, so disagreement between maximum entropy approach and factorizability to the problem of interactions. So now I turn to quantum mechanics, and I have to tell you in advance that there is no factorizability. We must rely on the maximum entropy approach. In the quantum mechanics, nobody has yet found a factorizability construction to describe interactions whatsoever. Fine, at least we have not seen, and in our group, I, for example, works very much on such things in probability theory. We did not come across it.
Can you sorry to interrupt, but so you don't lose me here completely. This is the interesting bit for me. So can you translate it into words, into simpler words, what that result actually implies in terms of, well, quantum, like, what you said, like, what would the factorizability actually give you in terms of quantum mechanics? What does it say about? I have a very computational view of quantum mechanics, not a probabilistic, not a quantum mechanics view, so I'm more into quantum computing, quantum cryptography, and I understand just the mathematical model as a sort of machine to do some kind of calculations. So it's far-fetched, but somehow it would be very interesting for me to understand what that non-factorizability or factorizability would actually mean.
There are some methods, as far as I understand, for example, tensor product, product states in quantum mechanics, how they are called. I'm not an expert in this field, which have applications in many models of physics and computation also. Right. But there's nothing known which actually caps the action in this form. So I don't know.
So does it say something about that you can actually factorize interactions or something?
So this would be very desirable, yes.
And that's the kind of question you're investigating.
Yeah, but this is a particle concept, and this symmetric tensor states, I think is the name. I will look it up if you're interested. This is a different decomposition. It has also, of course, you can say if you need more higher rank tensors to approximate a state, then it should be more complex in any sense. Yeah. But what we want to do is really to quantify interaction between particles.
Right, okay.
And then you have always to take into account, well, how you make precise, but it means that only k particles interact and not more of them.
Okay.
But this is difficult. And if you specify only the k body marginals and use maximum entropy, then you are somehow on the safe side, because you can say, okay, I have put in all information about the k marginals, so I know exactly what the state or the probability distribution does on subsets of size k. And since it's a maximum entropy distribution, it has no other information.
What about the Cohen-Specker theorem? So you can't have global marginals in most quantum systems. Question of dimensionality 2.
Okay, say it again.
So you can't have independent measurements of K particles.
We do not measure here.
So,
We do not process a measurement at this point.
Yeah.
or allocation. So, what exactly has been specified?
We want him somehow to make a model of what it means of particles to interact.
So, just thinking in terms of
Of
Hilbert's.
course, you can also make measurements which are non-local. I mean, we don't know exactly what you mean.
Well, so I was trying to relate this, the proceeding to quantum mechanics in terms of Hilbert spaces, for instance.
Yes, this is the idea behind it.
Okay.
And that, to my knowledge, I don't know, I would like to know your idea, if you have time to tell me later, how you can, what other possibilities exist to make this, to create a notion of interaction structures.
So there are Fock space representation of 1, 2, 3 particle systems,
Mhm.
many particle systems.
Yes.
And there is work on.
Of course, it's known as the K-local Hamiltonians. Of course, this is exactly the same.
And then
You can say this, but
there is a method, there's a work in the 1970s which describes dynamics of interactions in systems. Mark Hamiltonian, using some kind of Hamiltonian defined in this system. The interesting thing is that you can define so-called weak interaction, it depends on some parameter. And then the result is interesting that you can obtain a final equation. It's kind of like Boltzmann equation or Hierarchical equation, a nonlinear equation exploring dynamics of the system. And the nonlinearity of that equation, which is expressed as, for example, polynomial of power k. This polynomial, the highest power of polynomial k, is exactly the maximum number of interactions.
Can I come back to your question? There's another approach which is called finitely correlated states, which is due to Kahle and Werner and also from this. They try also something similar. So there are many approaches, but this is exactly what they do. What you can, if you have local Hamiltonians, then you take a chip state, a maximum-entropy state, a thermal state. This is exactly the same which I said is possible, but in the classical case of probability distribution, you have additionally the choice to write the probability distribution as a product. This is an additional feature which is absent, and maybe there's some alternative for this
So your product
linear or non-linear, I don't know.
Product, of course, you can think of it as exponent of some sum. Exponent of a sum you factorize into product, but because in non-commutative case, the exponent of a sum is not a product.
This is probably not commutative, yes.
If x and y don't commute, exponent of x plus y is
but I want to emphasize this is not a method to measure anything, just want a model to have a model of states which have restricted capacity of interaction. Model of low interacting states, which are governed by a particle number. At most 2 particles, at most 3, and so on. So now I continue with the probabilistic setting, but have in mind that we can always embed the probability distributions as diagonal matrices, and then we end up with density matrices, and so I just don't want to lose the probability theorists, and I would like to continue with probability theory and think please of both, because we have done some work on it. Maybe I can give you a citation at the end. I have not much material anymore, but it's Friday anyway. So higher order correlations are defined as a distance from the lower order correlations or lower interactions, and the distance is the KL divergence. In the quantum case, it would be in the Geiger relative entropy, and it's defined like this: the asymmetric distance, but it's only non-negative, and 0 only for equal arguments. And then this quantity here measures the distance from the exponential family of k interaction